Hello everyone. Today I would like to discuss a mathematics problem which I explored a couple of days ago regarding logarithms. In particular, I would like to explore how the logarithmic function changes as a changes. Okay, so quite handily, Desmos allows me to plot two graphs, the graph a to the x and the inverse function of that, which is the log of x with the base a. So what I particularly want to explore is at what point do these graphs intersect exactly once. Because if we notice, if, for example, a is 1.4, then we have two intersections which are quite clear on this graph. But if I raise it to 1.5, which is only slightly more, we have no intersections. So I want to explore and find the point, or the value of a, for which there is just one intersection. So there's just a tangent with these two graphs. Now, there are multiple ways I can approach this, but I want to find the exact value, so there is a particular course of action that I'll follow. But for now, I do know that it is between 1.4 and 1.5. Okay. Now, it is handy to note here that a function has an inverse of that same function, with the equation of which being just the reflection of the original function in the line y equals x. So basically what I'm trying to say is that the graph y equals log a of x and the graph of y equals a to the x are just reflections in the line y equals x, which is quite an important fact, and I will be coming to that quite frequently during this. So this is why the question I've framed quite differently. So we really should be finding the exact value of a, such that the curve y equals log base a of x and the line y equals x have just one intersection, and a is more than 1, obviously. Now, if a was less than 1, then it'd be very easy to have just one intersection between our two graphs. But unfortunately, we're trying to find just a very single exact value for which this is possible for a greater than 1. So this is what we're going to try to be doing. Because the two graphs a to the x and log a of x are tangential to one another, the graph of log a of x and the line y equals x will be the latter will be tangent to the former at a certain point. So that is the point which I want to explore, and I want to eventually gain the value of a from this. Okay, so we've already covered that the line y equals x would have to be a tangent to the curve y equals log a of x, and I've also covered the reasons for this. So a different way to express this mathematically with more rigor is that the derivative of the log of x, log a of x, is equal to 1 when x is equal to the log of x with base a. Now, this is important because we know that y equals x, and the graph that we have is y is equal to log a of x. So we know that any intersections would have to have this property. And this is the information that we're going to be used to move forward. The first thing, which is important to note, that to differentiate the natural log of x, which is just the logarithm with base e of x, we would get the answer 1 over x. And we can obviously write the logarithm of a. We can write the logarithm of x with base a using the change of base formula. So we can write it as the logarithm of x would base b over the logarithm of a with base b. So in this case, the base here will be e, so that's why we're using the natural logarithm. And using these two facts, we can actually differentiate the log of x with respect to a. So this does help us quite a lot. Right, so from this we can differentiate the logarithm of x to get 1 over x ln a. So and now we know that this is obviously going to equal 1 because the derivative of the line y equals x is always going to be 1, no matter what value of x. So that's why this value has to be equal to 1. This is also why this value is also set to 1. So because 1 over something is equal to 1, we know that x times ln a must be equal to 1. So we'll move forward from this. Now, from this we can actually use some information that we've had previously. So x is equal to log a of x, as we've already covered. So we know that the log of x with base a multiplied by the natural log of a is equal to 1. But how can we write the logarithm of x with base a? Well, we can use our same change of base formula to get ln x over ln a, so that log a of x multiplied by the natural log of a is just equal to ln a times ln x over ln a. And now the ln a's here cancel out, so we just get ln x is equal to 1. And that makes things very simple, because we can just raise e to the power of both sides, and we get a is equal to e. We get x is equal to e, which is a very important step in this scenario for finding out the value of a. So from this, things become easy. So e is equal to log a of e. Notice we've actually just used substitution from x is equal to log a of x, because obviously x is equal to e. So we have this equation here, and this implies that a to the e is equal to e, because we've raised a to the power of both these sides. So a to the e is equal to e, and then we take the eth root of both sides to get simply a is equal to the eth root of e. Now we can obviously represent this in a different way. We could represent it as e to the 1 over e, but a lot of people would actually prefer this way for some reason. So it's quite this problem is quite handy, because you'd initially think that you would have to use the lambda w function to solve for a, because you might expect us to get something like x times ln x is equal to a constant. But no, we actually can use this. We can actually use early A-level kind of knowledge to solve for these kinds of problems, which is what makes it quite interesting if things can be solved simply when they don't seem like they can. So I hope you've enjoyed this demonstration, this proof, and I'll see you next time. Thank you.